Welcome to Life with David. I'm David, and today I'm continuing my adventure into assembly programming of the RP2040. I know I promised some debugging information, but several viewers really wanted to learn how to run assembly language programs without using the C++ SDK. I had acquiesced to using the SDK to get my bare metal journey started, but that was only after spending many unsuccessful hours trying to do it without the SDK. But I'm bullheaded enough that when others request it, I'll do everything I can to ditch the SDK. It took many more hours of study and trial and error, but I finally got there. So why don't you join me as we do some truly bare metal programming on the Raspberry Pi Pico. The Raspberry Pi Pico is an amazing little microcontroller. There are several more capable microcontrollers out there, but the Pico and the RP2040 have arguably the most comprehensive software and information support of any of their rivals. The brilliant software engineers at Raspberry Pi Trading Limited put together a suite of software tools to help embedded designers efficiently develop applications for the RP2040, the C++ SDK. The capabilities of this SDK are wide-ranging, but as a result, there's lots of overhead. For instance, my first assembly language demonstration, the LED blinking program, used the SDK to initialize the assembly program. The main program was just 64 bytes long, but the SDK overhead consumed an additional 12 kilobytes. There had to be a better way to get down to bare metal software support. To understand where and when we can grab control of the microcontroller, let's look at the RP2040 boot sequence. According to section 2.7 of the RP2040 datasheet, after power on, the RP2040 waits for a stable power source and then starts a power on state machine that initializes clocks, memory, the bus fabric, and several other boot critical resources. Then both cores enter the first stage bootloader, which starts core 0's initial boot sequence, puts core 1 in a low power wait and launch protocol, and initializes a USB first stage bootloader with UF2 support for downloading code and data into flash or ROM. Other programs on the boot ROM included a USB Pico bootloader interface for advanced management, routines for programming and manipulating the external flash, a fast single precision floating point library, fast bit counting manipulation functions, and fast memory fill and copy functions. All this is burned into the RP2040 read-only memory. The first stage bootloader will execute every time the microcontroller is powered up. As you can see from this memory map, the boot ROM is located at the very bottom of the memory map, starting at address 0 hex. The goal of the first stage bootloader is to enter the second stage bootloader. This can happen in a couple different ways. As soon as the RP2040 is powered up, the first stage bootloader will check to see if the boot select button is pushed. If it is, then the first stage bootloader will use the USB connection to load a UF2 file into flash and/or static RAM. This includes loading the 256-byte second stage bootloader into the very beginning of flash at 10000000 hex. If the CRC32 checksum at the end of the second stage bootloader is valid, it will branch to the beginning of the second stage bootloader. If the button was not pressed, the first stage bootloader will alternatively start by checking the CRC32 code located at the end of the second stage boot ROM image in flash. If the code is valid, then the processor will branch into the second stage bootloader. If the code isn't valid, the first stage bootloader will wait for valid software to be loaded via the USB connection. So what does the second stage bootloader do? According to section 2.8.1.3 of the RP2040 datasheet, its only job is to configure the synchronous serial interface, or SSI, for the best possible execute-in-place flash performance. Alternatively, it could move a copy of the software in flash into static RAM and execute it from there. What happens after the second stage bootloader has completed? Well, that depends on the bootloader. Several second stage bootloaders have been written to accommodate different types of flash memory, or even for using static RAM only. The second stage bootloader supplied for the Pico accesses information from a vector table located at 10000100 hex to branch into another routine. The first word of the vector table is the stack pointer address. The second word is the address for the start of the next routine. When using the SDK, this all happens behind a magic curtain. But I wanted to go into really bare bones without using the SDK. So it took me days of research and reverse engineering of the boot code to figure it out. At the same time, I needed to learn how to use make, linker scripts, GCC, and create UF2 files from ELF files. But now I have all the tools, so let's make an LED blink. I'll use the same assembly program that I used in the first chapter of Bare Metal Adventures. As a quick refresher, this program resets IO bank 0, configures the output pad as a GPIO output, enables GPIO 25, and then sets and clears the output bit for GPIO 25. Please see Bare Metal Adventures Chapter 1 for more information. In addition to the assembly program, I'll need to load the second stage bootloader and a vector table that contains the starting address of our assembly program. I'm going to use the same second stage bootloader that the SDK uses for the Pico. I found it in the build folder of any of the previously compiled projects. Just search for BS2 default padded checksum. For the vector table, I just made a list of 48 words, but the only ones that matter at this point are the first and second words. I'll go into more detail about these files later, but for now, I'll put a link to them in the description below. Next, we have to compile the programs. Use ARM, none, EABI, GCC, -C, -mCPU equals Cortex-M0 plus, -mthumb, -std equals GNU11, -WALL, -O0, assembly.s, -o, assembly.o. This part invokes the GCC compiler. This part stops GCC at the compile stage. It does not continue linking the files. This part specifies which processor, thumb versus full ARM instructions, and the GNU version. The -WALL will turn on all warnings and errors to help debug the compiling process. The O0 means that we will not optimize the code at this time. Our input file goes here with the output file as specified starting with -O. This has to be done for each of our assembly files. We can make our lives a lot easier by creating a makefile which automates the compiling and linking process. In this case, the makefile is relatively simple, so we'll create it manually. Don't get too worried. Creating a simple makefile manually is much easier to understand than working with CMake, which is much better at automatically creating the complicated makefiles needed for the full SDK. I'll give a quick tour of the makefile I used for this video. However, if you want more information, there are several videos on creating a makefile. I'll put a link to one in the description below. I'm using Make for Windows. Simply search for Make for Windows and click on the link. Then in the description, click on the Setup Program link, which will download the file. After you install and set up the program, you may have to add the Make installation folder into the path statement. My makefile has these variables. CC is the GCC compiler call. MACH is the processor, in this case the Cortex-M0 plus. CFlags contains the options we're using for the compile stage. LFlags contains the options we're going to use for the linking stage. Next is the All option, which lists each of the target files. assembly.o, bs2 default padded checksummed.o, and vector tables BMA04.o. Under each of those target dependency pairs is the recipe to create the target file or $@ from the dependency file or $caret. The -o indicates the output files. The command issued to GCC is arm none eabi gcc -c -n-cpu equals cortex m0 plus -mthumb -std equals gnu11 -wall -o0, the dependent name .s -o, and the target file name .o. Just like the standalone command I entered earlier, -c means compile only, don't lick it this time. The processor is Cortex M0 Plus. Use thumb instructions, use the GNU version 11, list all warnings, and do not optimize the code. Now we can compile all 3 files by entering make all at the command prompt. Entering makelink in the command prompt will link all 3 of the object files above into final.elf. Here we use the linker options contained in L flags. The command issued to GCC is arm-none -eabi-gcc -no-stdlib BMA4_ls.ld -wl, -map equal final.map -o final.elf bs2_default_padded_checksummed.o vector table _bma04.o assembly.o, where no standard libraries will be loaded. The linker script bma04_ls.ld will be used. I'll get into much more detail about the linker script shortly. These are the dependent files. The output file is final.elf. And the linker is instructed to produce a .map file named final.map. I've included makeClean, which deletes the object, elf, uf2, and map files from the project folder. This just saves time while debugging the program. Finally, we need to create a uf2 file to load the second stage bootloader, the vector table, and our blinker program into the Pico. Make sure the executable elf2 uf2.exe is located in the project folder. The make shortcut is make uf2. The command issued is elf2 uf2 final.elf final.uf2, where elf2 uf2 calls the executable. Final.elf is the output of the linker program and the input to this program. Final.uf2 is the output of this program. Okay, let's try it out. Using the command prompt, I'll navigate to the project folder. Then I'll run make clean to remove the old files. Next, I run make all to compile all 3 assembly files. I'll use make link to link the 3 files into one ELF file. Finally, I'll use make uf2 to create the uf2 file for loading into the Pico. I'll load the program just like all the other ones, holding down the boot select button while connecting the Pico to the computer. Then I'll drag the uf2 into the RP2040. Just like we hoped, the LED lights up. But why isn't it blinking? Oh, it is, just very slowly. That's because we haven't set the processor clocks to run at full speed. In fact, the default clocks are at least 10 times slower. That's something we'll address in a later chapter of Bare Metal Adventures. This demonstrates we can run a program without relying on the C++ SDK. The total size of the blinker program, including the second stage bootloader and vector table is 588 bytes. Compare that with the same demonstration using C, C++, which consumes 7,740 bytes of flash and 4,192 bytes of static RAM, even though the main C and assembly programs only occupy 64 bytes. Let's get into some of the details we skipped over during our demonstration. First, let's look at the second stage bootloader. We used the BS2 default padded checksummed.s that we found in any of our build folders of previously SDK compiled projects. But where did it come from? Well, if we go into the C, C++ SDK under the SRC RP2 common boot stage 2 thread, we find source code for a number of different second stage bootloaders. These bootloaders were written to accommodate the wide variety of flash memory chips that could be paired with the RP2040. The flash memory used in the Pico is the WinBond W25Q080, which has a corresponding second stage bootloader named boot2 W25Q080.s. When using the SDK, a binary file for this bootloader is created during the initial CMake process. Then the binary file is run through a Python script called pad checksum.py, where the binary file is padded to 252 bytes, and then a 4-byte CRC32 checksum is calculated and appended to the end of the file. This second stage binary bootloader file is then converted back into an assembly language data file named BS2 default padded checksummed.s for use in subsequent compilations of the project. You can write your own bootloader. All you have to do is compile it, link it to start at 10000000 hex, and then run the binary through pad checksum.py. The Pico bootloader uses a helper function to exit the bootloader named exit from boot2.s. If the second stage bootloader was entered from the first stage bootloader, then the exit function will grab the value of the first entry of a vector table that starts at 10000100 hex and load it into the stack pointer register. Then it grabs the second entry of the vector table and branches to that location in memory. That's the start of our blinker program. Now let's look at the vector table. The first entry is the start of the stack pointer, and the second entry is the start of the reset routine. Since we are going to go full bare metal, I'll use the start of the reset routine as the start of the blinker program. The rest of the vectors come into play for more sophisticated programs that use interrupts. The locations are described in the file crt0.s. I want to point out a subtle but important item in the vector table. Note that none of the vector addresses except the first end in an even number. Even though the actual addresses of any program must end in an even number, the vector table addresses end in an odd number. That's because indirect addressing in thumb mode must have bit 0 set. This can lead to errors. Don't ask me how I know. Anyway, I want to start the blinker program at memory location 10000200 hex. To properly utilize thumb mode, I put the address 10000201 in the vector table under the reset entry. Now we need to modify the linker script to put all the binary files in the correct spot. I started with the SDK provided memmap default.ld linker script and modified it. I'll do a quick tour. For more information, I'll put a link to a good video on linker scripts in the description below. We start the linker script with the memory command. Here the Pico has 2 megabytes of read and execute flash memory starting at 10000000 hex. 256 kilobytes of read, write, and execute RAM starting at 20000000 hex. 4 kilobytes of read, write, and execute scratch X RAM starting at 2004000 hex, and 4 kilobytes of read, write, and execute scratch Y RAM starting at 2004100 hex. The entry command is optional, and it's set as entry point. Although I don't need the entry command for this project, I kept it in so we could use this linker script as a template for more complicated projects in the future. The sections command is where we define where the various files will all reside in memory. Here I started out with the section flash begin. The location counter, denoted by a dot, identifies the current location of memory during the linking process. The location counter automatically points to the beginning of flash memory, and I captured that location with the linker script symbol flash binary start. Even though there's no data that will go in this section, I still indicate that the virtual memory address, or VMA, and the load memory address, or LMA, are the same, and both are located in flash memory. The next section is boot 2. But how does the linker script know what is in boot 2? Well, there's a section keyword in the assembly program that designates the code following it as boot 2. Going back to the linker script, we'll set the linker script symbol boot2 start to the start location of the boot2 program. Then we'll tell the linker script to keep the section boot2 in the project map even if there's no contents in this section. However, this time we do have the boot2 file, so this will be assigned memory location 10000000 by the linker. We'll create another linker script symbol, boot2end, to signify the memory location at the end of boot2. Then we'll set the VMA and the LMA to put the file into flash. Show a little bit more. This statement will throw an error if the boot2 is not exactly 256 bytes long. The next section is text. Here I'll create another linker script symbol, binary logic start, to capture the beginning of the next section. In the text section, we'll include vectors, which is where the vector table will reside, binary header information if we had any. We don't, so this section will be empty. Next, we set the location counter to the start of the vector table plus 100 hex. This results in a memory location of 10000200 hex. This is where we'll put our blinker program that we have designated as reset. Now, I could have called this anything as long as I was consistent between the program and the linker script. However, I didn't want to make too many changes at first. Finally, I set the VMA and LMA both to flash memory. Now we've located our 3 programs, the bootloader, the vector table, and the blinker program in memory. We don't need the rest of the linker script at this time. However, I'm keeping it as a template for more complicated projects, which I hope to get to in the next few videos. Thanks for joining me today. We went full bare metal by ditching the SDK and running a simple blinker assembly program. We learned how to use second stage bootloaders, vector tables, and linker scripts to take control of the RP2040. It was a lot to cover, so you might have more questions. Let me know in the comments section. Next time, we'll get a little deeper and I'll try to address your additional questions. I hope to get into resetting the clocks and perhaps using the UART, so stay tuned. If you like this video or you think someone else might, please give it a thumbs up. If not, give it a thumbs down. The more likes this video has, the more YouTube will recommend it to others. Also, please leave a comment or suggestion for things to do. I hope to do more of these videos, so please subscribe and click on the bell for notifications of new videos. Let's get together next time for another day in Life with David. See you soon!